Oh, hi there. I'm Tim. Have you ever wondered if you could pop popcorn by dropping it off the top of James Height? In this video, we're going to explore some of the concept behind that idea. We're going to start by assuming a closed system where all the potential energy of the kernel is converted to kinetic energy. As the kernel hits the ground, this kinetic energy is going to transform into a change in internal energy. We're going to assume that this change in internal energy is going to be directly the result of not quite sure how to spell it, that's okay. Temperature effects. We're also going to assume that the change in internal energy can be approximated as delta H. When we do an energy balance for the system, we get that the overall change in energy is going to be equal to the negative change in potential energy. The popping of popcorn is due to the moisture inside the kernel. As this heats up, it expands and turns to steam. This causes the skin of the popcorn to rupture, and you get a big pop. We're going to be assuming that any heating that happens is only going to be happening to the water inside the kernel. Though some popcorn will pop at 100 degrees Celsius, most of it won't pop until 230 degrees Celsius. This is when the pressure is going to be much, much greater, and that will cause a much more violent pop. We're going to assume that the mass of water inside the kernel is equal to 1 gram, heat capacity equal to 4.18 kilojoules per kg, ambient temperature equal to 20 degrees Celsius. Final temperature is going to be 230 degrees Celsius, and we're going to assume that ZF is ground level, which is 0. Our assumptions are that the change in internal energy is only due to the temperature, that the constant volume heat capacity is the same as the constant pressure heat capacity, and that the change in internal energy is equal to the change in enthalpy. A change in internal energy can be given by the sensible change in enthalpy plus the latent heat of vaporization. Putting in our numbers there, we get that the change in internal energy is equal to 3.1425 kilojoules. Equating this to our equation for potential energy, we can rearrange and we equate the two. We find that our initial height is equal to 320.3 meters. Our 320 meters that we calculated for the popcorn to pop just by falling is comparable to the Eiffel Tower and the Sky Tower in Auckland, much, much bigger than the 53 meters of James Height. Now obviously, if you throw a piece of popcorn at the top of the Sky Tower, it's not going to pop on the way down. That's because we've made several assumptions to our model, and a lot of them are going to have a huge impact on whether or not this actually happens. The biggest assumption to start with is that we're going to be losing a lot of energy to the cool air as it falls. Obviously, it's not a perfectly insulated system, so you are going to lose heat and energy as you go through the air. You've got to heat the rest of the kernel. Obviously, we've only considered the water in the kernel in our model, so it's not quite representative of the whole system. We've assumed that all the kinetic energy is being transferred to internal energy. That's not the case. It's not going to be a perfect translation, so that's going to affect the numbers. The kernel is also going to have a terminal velocity, which is probably quite low for a popcorn kernel, and so as a result, once you reach the terminal velocity, your V is not going to change, and we're not going to be able to get any more kinetic energy getting translated into the popcorn. Hey guys, this has been Thermodynamics with Tim. I hope you learned a thing or two. Hope to see you around.